Okay, thanks everyone. Thanks for staying for the last talk. So this talk is not connected to the previous talk by topic, so it's not about the fusion model, but it is about stochastic dynamics, and so there are similarities in the words that I will use. But the difference, stochastic and how should think about stochastic gradient descent with observable consequences, so to say. And so this is work done with my student Chandu Park, who's here in the audience, and Olivier Vicini, and then also at the end a little bit work with Johan. And it's based on the papers you see. And so the topic is random matrix theory, and random matrix theory is very old. It was developed by Wigner and Dyson in the late 1950s. The first spectra, and that has been since then to many directions, and because it describes universal behavior of matrix quantities that fluctuate, so that's why it's so widely used. And I came across it first in QCD, where it describes the eigenvalues of the Dirac operator and the universal fluctuations. So it's really but in this, I want to describe to machine learning, because that's the topic of the workshop. And really, well, I mean, this slide has a lot of obvious things, especially after all the great talks we had in the previous days. Of course, in a neural network, you have layers of nodes, and the nodes are connected by weight matrices. So that's where the matrices come in. And then during training, the weight matrices are updated, usually, for instance, stochastic gradient descent. So that's where stochastic comes in. And if you have stochastic matrix dynamics, then kind of what's called in motion, which would then lead you to random matrix theory. So there's a really direct path from stochastic gradient descent to that in random motion and then to universal features. And that's what we'll discuss in this talk. And there are, well, two reasons to do this. One is to further understand learning, not in terms of everything we heard in the past 2.5 days, but also by thinking about matrix dynamics in terms of these words. And second, these fluctuations that dynamics, these are things like level spacing, cushion thickness, and the question is how these universal features appear in stochastic gradient descent and how they will affect your learning and your quality of learning. So that's the aim. And like yesterday, please interrupt if you want to. I don't think I need a full 1.5 hours, so you don't have to be worried. And but if you interrupt a lot, of course. Okay, so I'll say so. Just make the link to Dyson-Brownian motion and the Coulomb gas description. And then it turns out there is a very nice universal property that just falls out of the formalism when you apply it on the stationary distribution. So we'll discuss that. And then verify this universal behavior in the restricted Boltzmann machine, which is the simplest kind of neural network. Say, because even in the GAN restricted Boltzmann machine, and that's essentially exactly solvable. So we can really see all these features appearing there. That's the plan of the talk. Okay, so very general stochastic weight matrix dynamics, stochastic gradient descent. You take your typical neural network, and you have some weight matrix, which are denoted with W. In general, they are rectangular, and we update it with something like stochastic gradient descent. To learn gradient alpha. And in practical applications, you do the update by averaging over some mini batch. And this is denote the batch with curly B and then the size with absolute value. And so in every update, you you estimate your update step by taking the average over a batch size, which means that it has a mean also set finite batch size. So this is using the central limit theorem in yet another way. And basically, if you take your batch size to infinity, the fluctuations will go down. And if you take the batch size very small, there will be a lot of fluctuations in this. And so the way to think about stochastic gradient descent is not by starting from, it's not by thinking just about this equation, essentially, by having this fluctuating term in the update there. And so there is a random vector, a random noise element here, eta, on the normal distribution, so that the variance of this update is indeed behaving like this. And so the rest of the talk, when we say stochastic gradient descent, we mean it in this way. There's a kind of, say, quote unquote, this is very general. So the update was given by the gradient of the derivative of a loss function. So I insert these quantities here, and they appear as follows. So the derivative goes with the learning rate, and this is the variance, or the square root of the variance. So it goes with the learning rate, and then there's the square root of the batch size in the denominator. Now, so this is our basic equation with which we will study out.
So when we do this, do we lose the covariance here, or is this like entry by entry?
Entry by entry, exactly. Entry by entry. This equation has really ij and dc's. We made this with the indices. Okay, so this is the basic equation we start with. W is, as I said, in general, it's a rectangular matrix, and random matrix theory is typically for square matrices, symmetric matrices or emission matrices. And so we want to go to use symmetric matrices to make the connected theory, and we'll do that taking W times WT or W transpose times W. That obviously makes it symmetric and square. And then it's also useful at this point to introduce a single value decomposition. So the rectangular matrix can be decomposed like that. This big psi denotes the singular values here. So there are n of them. I always take n less than n. Then times W, then these singular values appear on the diagonal like as a square. And so these are the eigenvalues that I'll consider in the random matrix analysis, and these are called by x. So the singular values are psi, square of the single values are x. And then if the original W matrix satisfies the equation from the previous x equation, that this is symmetric. Symmetric. And this is convenient because, okay, before we go to random matrix theory, let me say one thing because I'll use this throughout. When you initialize your weight matrix from the normal distribution, like in this morning's talk, then the matrix element from X, or the eigenvalues of X, satisfy this Marchenko-Pastur distribution. This X flow. And there's some parameters in here. So R is the ratio of the size of the matrices, so N over M. And the variance appears there, sigma squared appears here. And the M is because I'm just really taking WT times W, I'm not dividing by anything else. And so then there's a little bit of freedom to choose the variance and choose without encountering any problems. And so it's kind of obvious then, I think this is exactly what Boris mentioned, to choose the width as 1 over M here. Because then this Marchenko-Pastur distribution has no dependence on the scale anymore, yeah.
So what are you taking from this variance matrix? Identity at the end of the day, or are you keeping it general? I guess not. constant over the different indices, or?
No, it will actually just be determined. So when I in the calculate, no. So there are just the indices ij are here, so it can vary, fluctuate as it wants. And in the numerical simulations, we'll just update the weight matrix using stochastic gradient descent, so it will just fluctuate as it does in the simulation. So there's no constraint. No. So it's a some relation used in fact between diagonal of diagonal elements just to make the algebra go nicely. But the numerics will be completely just standard stochastic gradient descent. Yeah.
But we need sufficient independence between the entries for it to give you the XXT to give you a Mashenko plus store, similar to when you derive Wigner.
I don't think so. I think if these matrix elements of elements
Yeah.
Yeah. But upon initialization, that is satisfied.
This slide. Delta XP is what you get from the stochastic gradient descent, right?
Yeah.
And then the other term is just that noise that you have so that you don't end up in a also.
Now we don't add the noise. The thinking is that if you batch, there will be fluctuations there. So in the numerics, we just take this standard gradient descent without adding any noise. But by taking an average over a mini batch, the fluctuation space will be inherent.
So just to understand, moving in various directions in some landscape,
Yes.
and averaging over those, how are you picking the directions?
So the average here is over the data set. So we take many switches from within the data set. That's the only average here. And if you do a mini batch update, the fluctuations are inherent in that update, basically. So
maybe since we'll do the later. So I initialize, and now we're discussing, let's say, the first step after that.
yeah.
So do I?
Initial way, so if we have the initialize my network or my Boltzmann machine, which I'll discuss later, just with random, from a normal distribution. I happen to choose the variance in such a way that all this goes for out. Then I just use standard stochastic gradient descent, where this gradient is over. Yeah.
Got the loss function,
I go down.
and calculate this exact gradient. Also, fluctuations that have been picking different, estimating the gradient by using different.
Exactly, that's where the fluctuations come in. Yeah. So if I would take the whole data set in every step, you could imagine that I would go straight down. But now, because the mini batch is small, I go down in a kind of random fashion.
So the resides in this.
Yeah, so the larger the batch, the smaller the fluctuations, which is just taken from the central limit.
Well, let's say if I was thinking of linear regression, do I, think of small x values to large x value that I try and spread? Is it like election set polling? You try and pick a sample which is representative throughout the data set?
You assume that all your elements in the data set are identical, come from the same distribution. We link with all yeah, so I don't think we pay particular people.
You give you a data set is big enough.
Yes, we also like data set. So assume there's an infinite case. But so the whole point, I guess, is so the questions are very good because the whole point is that the actual numeric from data. Nothing is added. We want to analyze standard mini batch stochastic gradient descent using random matrix Dyson routing motion. Alpha is the learning rate. Eta is just a random variable. No, eta represents the fluctuations of the update using the central limit theorem. But we don't update the system using this. This is the effective description of physics. And so the picture is that during this evolution, the weight matrices will evolve. And if we start with weight matrix element from the normal distribution, the eigenvalues of this symmetric matrix X W transpose W will follow the Martenko-Pasteur distribution. And as the system learns this. So now let's make a connection with Dyson-Brownian motion. So what we have is a stochastic process for a symmetric matrix. A real and symmetric matrix. And that formalism says the following. It's written in continuous time here. I'll come back to that below. If I update my matrix elements here with some drift term and some noise terms, also some stochastic update, and the strength of the noise is given by this coefficient here, then the eigenvalues will evolve equation where the I introduced already. The drift term is essentially the diagonal part of the drift in the matrix. And now there is a subtle thing about the correlation between the fluctuations of the diagonal terms. Basically, it's assumed that the update is drawn from a random distribution. And that means that the off-diagonal terms, which appear here, this is essentially J is that they. And that says that the update, this matrix here, comes from very much what Jim was writing in the morning, e to the minus half trace made ATA. Yeah, so in the algebra, it's convenient to simply say that we denote this with the same letter here, because that's what we will need actually in the next page. No, they're not zero. So I should write, in that sense, I should write this a little bit better, that if you do this derivation, the Coulomb term, J is not equal to I, is actually Gij squared, Xi minus Xj, and the noise term is Gii beta I. And I simply, then these atoms from Fusion, which is something like a half trace ATA, which relates this one also to this one. So this one is also then.
So A is also random taking.
Exactly, and that's right. In the standard, in the vanilla Dyson-Brownian motion, A is also random. So that's why in the dynamics, A is not completely random because it comes from the update, but this is the formula to start with. Now, the crucial term that's here, if you don't matrix, you just tell you that there is this additional term here, which is a Coulomb propulsion. And so this provides an additional term in your stochastic update if you just look at the eigenvalues. Now, you know this term actually, well, if you're a physicist, you know this term very well, because this you can just derive it using second order perturbation theory in quantum mechanics. Because if you do quantum mechanics in matrices, then if you do second order perturbation theory, the energy splitting is essentially EI minus EJ, J equal to I. Same. To update your, if you do second order perturbation theory in quantum mechanics, this is exactly what you find for the second order.
So K is the derivative of Fusion distribution.
K is the derivative of, it's basically the derivative of the loss function, but constrained on the diagonal. Yeah. I call something like minus alpha dl dwij. And then we go to just the diagonal of that, that is the drift. In the derivation, basically you assume you're on the diagonal basis, you do one update, the eigenvalue updates by this quantity and the of the eigenmoment. Now the crucial thing here, of course, is that this Coulomb term is there and it leads to eigenvalue repulsion. And this is why it was introduced by these people. So
And how do you see the Wisher distribution coming out of that if I don't have a loss? So it should give you the Wisher distribution, do I understand correctly?
if you don't have a loss, now just be random with. So the Wisher distribution is
So this is not for X, this is for W itself.
no, this is for X. This is
But
for
X is W transpose W, so
Yes.
it should have a Wisher distribution.
yeah. Which one is the Wisher? Is it not so X is WTW?
So X should be Wisher.
Yeah, and so I call the eigenvalues of X Xi and the singular values of the X. So the relation.
But then this equation should converge. This stochastic equation should converge to a Wisher distribution if you don't have K.
If there's no drift, I would not definitely say yes to it because I don't have the answer, but yeah. But which one is Wisher?
Wisher is the positive one.
I see, but this one, yeah, this one is also positive, so okay. Anyhow, so but there's a little yesterday we have an equation, and so we can also write down the Fokker-Planck equation for the distribution of eigenvalues. And so this is really the same equation as I derived yesterday. So this is for the distribution of all the eigenvalues as a function of time. This is again the strength of the noise, like yesterday, and this is the drift. So it's staying the same setup. And then station. So if we put this K effective, I've written in such a way that it includes this Coulomb term. And if you then look at the stationary distribution, this is a stationary distribution. So in the measure, you find this difference between the eigenvalues, absolute value, and that reflects the Coulomb term, because in the dynamics, the eigenvalue goes to zero, the eigenvalue goes inside. And then there is a potential which basically assumes that you can integrate the drift to a potential. So to turn around, if we can derive the drift from a potential, then the stationary solution can be written in this way. Another way to see the Coulomb repulsion here is started as the of this symmetric piece. You go to the eigenvalue basis, you have a H measure, and for real and symmetric matrices, the H measure has this form. It would be Hermitian, there would be a power 2, for instance. And so it basically, what we are describing is the dynamics, or well, in this case, a stationary distribution on the space of matrices, but reduced to the space of eigenvalues. This is known as and it essentially describes universal features of random matrices. If your matrix is really just from an orthogonal ensemble, then the potential here is just quadratic, because the eigenvalues appear as quadratic. So x transpose x, so it's quadratic here, but it can be generalized. Okay, so that's the in a nutshell. Go back so to the wave matrix dynamics. So we have this equation there. It has very much the same form, and so we can immediately map it to the eigenvalue. So there's the eigenvalue equation. There's a Coulomb term. There's a noise term. There's a drift term. And if we now look just for scaling, look at the learning rate and batch size. This update here comes from this drift, which is learning rate times drift, and this function g comes from the variance of the gradient of the loss function, if you go back to the beginning, this scales with learning rate of the square root of batch size. Introduce quantities everywhere which are independent of those quantities. So the quantities without a tilde depend implicitly on learning rate and batch size, and the quantities with a tilde are independent. So if I insert these quantities in the update equation, it looks like that's this particular form here. And that's quite interesting, really, because we have it here learning over batch, here learning rate over square root to batch size. Yeah.
Sorry, I didn't quite follow previously. So when you're talking about GI and so GIJ, like on the whiteboard,
Yeah.
then to make this assumption that you can go from GIJ squared to GI squared, something about coming from a distribution of half raised 88, is that satisfied?
Yeah, so this is, I think this is story when you look at the actual dynamics, the actual numerical simulations. But a priori, you wouldn't know exactly how the fluctuations of the gradient of the loss function, how these are correlated, the diagonal elements. I think you don't know in a real simulation if how well they are correlated, say. But it turns out that this assumption is fine. So this is Fisher.
Particularly, I think that if you're getting near a minimum, certainly, I would imagine things might look different there. As opposed to starting near the top of the landscape. Have you ever tried tracking?
Yeah, we do the whole, we go through time, we do the whole time dependent process. So
The statistics look.
So the point, yeah, I guess the point I'm making is that this set of stripes are numerical experiments very, very well.
Markov systems is ETH, which is similar in spirit, right? Which is nearby eigenstates and random matrix stuff. The middle of the spectrum here, that's the thought in my head about.
Okay, I can't, I can't answer. So let's see what happens. So the first observation is that naively we think that the learning rate is like a step size. So if I take the learning rate to 0, I end up with some kind of continuous stochastic rate. If I take the learning rate to 0, this term drops out, for instance, and these terms scale in the same way in alpha. Whereas if it would be a proper stochastic differential equation, we would want this term to scale with epsilon and this with square root of epsilon. So that simple scaling, naive scaling doesn't quite work. You could say, well, maybe the batch size is like epsilon. So 1 over the batch size. So this is 1 over square root of batch size, like square root of epsilon, and this is epsilon. But then this term doesn't drops out, basically, or doesn't scale in the same way. And so quite interesting. Like a continuous time equation. And that actually had been observed before in these papers here, also by Jaida, that there is only a kind of continuous time limit of stochastic gradient descent. It's a kind of weak sense where you can kind of close your eyes and write this just as a continuous time derivative, but you kind of have to keep the learning rate and the batch size explicit. Below in a minute that this is actually a blessing, because if I would take either of these limits, either associate alpha with the learning rate or the inverse of the batch size, one of these terms would drop out and I would lose this kind of interesting dynamics between these 3 terms. And so it's actually, in a way, convenient, or it's a blessing, as I wrote here, that this scaling is surface. But just, one of the take-home messages is that we all talk about stochastic gradient descent in continuous time and say we just have some equation, but this is not thing, so to say. Now let's look at the stationary distribution. So this is again this Coulomb gas with the Jacobian and the potential. And if I insert the learning rate and batch size explicitly, this little g came from the variance, so it scales with alpha over square root of batch size. The potential came from the drift term, and the drift term deals with the learning rate. Actually scales, so this scales with alpha, this scales with G squared, scales with alpha squared over batch size. So this combination just scales with alpha over batch size. And then the tilde quantities here are independent of those. And so this scaling is such that there is this kind of complicated dynamics that's on the top, is complicated outside kind of in a kind of funny way. If you go to the Coulomb gas description, we just combine in this linear combination. And if I'm then close to a minimum, for instance, so let's suppose indeed I have some well-defined minima and the eigenvalues evolve to the minimum and I can expand around the minimum with some curvature here, then you get this nice description where you're essentially this usual scaling term, which depends on learning rate and batch size, and then this model-dependent term, which depends on the curvature of your potential and your variance of your loss function. So it's a very neat experiment. Now, so after all of this, all we encounter is just the dependence of learning rate over batch size, and in fact, that has been seen that if you want to train your neural network very efficiently, you should not decay the learning rate, but you should increase the batch size. And so this so-called linear scaling rule, linear scaling relation had been observed just by running your code, changing alpha, changing batch size, and see what happens. And so the statement is that if you use this Coulomb gas description, and I should say that we were not aware of any of these papers. So it's a prediction of a post-paper. They were seeing that if you halve your learning rate and you do the numerical experiment, and then you repeat it, but you double the batch size, you get exactly the same loss curves and the same efficiency. One.
Typically, this holds up to a threshold that's can be derived in other random matrix theory frameworks and also just in traditional optimization. Does that threshold also come into your equations? Do you understand?
No. This is the most general statement I will make, but I won't.
Yes, at some point the curvature problem takes over. Did you expand this also to different types of stochastic gradient optimizers like Adam?
No, well, so one numerical experiment at the end is using Adam, and then of course it becomes complicated because both the show experiment where we can independently learning rate and batch size. It's not adaptive. So to really so this drops out. But of course, as soon as you make it all adaptive, then you lose control. Really.
What is the functions with these synthesis and the eigenvalues? The way what can you say something about the curves?
Yeah, because in this stochastic equation for the eigenvalues, even though it looks like the way the learning rate and the batch size appear is pretty much all over the place, when you formulate it as a Coulomb potential description, where the drift follows from the Coulomb potential, then they combine just in this one combination here. So this particular form in the top there is alpha and then alpha squared over batch size and alpha over square root of batch size. They conspire to a Coulomb potential where the only place where alpha and batch size appear is then in this ratio. So I want to because it's can only into a bit of a priori a bit. these papers, of course, do a lot of very advanced things. Okay, so that's so now so that our statement, if you describe weight matrix dynamics using Gaussian Brownian motion, and you make these few assumptions on how the elements fluctuate, then the kind of statement is that learning rate over batch size is the one quantity that. So now we will apply it to some models, and we use a very simple model because that's a model we started with. Very easy. So talk about this of Dyson Brownian machine in this context. And so what's the Boltzmann machine? It's a neuron with 2 layers and 1 weight matrix. It's not a forward network. It goes what goes in comes out again on the same side. So this is a visible layer and this is a hidden layer. The number of nodes is called NV for the visible layer and NH for the hidden layer. They don't have to be the same. And so in general, the weight matrix will be rectangular. You can use it for generative purposes. Trade on it, and this data will generate more next pictures. The piece of freedom here can be binary, and Dimitrios stored they binary, but they can also be continuous fields. And it is an energy-based model, so there's a probability distribution that lives on both of these sets of nodes. And so if you take continuous fields, you can think of this, and this is why we started with this. You can think of this as a field theory with 2 types of fields which talk to each other between the layers that don't talk directly to each other. And I found it convenient to think about it like this because I'm more used to thinking about that as field theorists than about other things. So this is a field theory with bilinear interactions. If I take the fields to be Gaussian, then it's the Gaussian theory, Gaussian lattice field theory. And you can have a mass parameter for the phi field, which is the visible field. You can have a similar mass parameter, but for future convenience, write it as 1 over sigma squared with subscript h for the hidden field. You can introduce a source term or a bias. And then there is this bilinear coupling that couples the hidden and the visible fields, which is matrix W. So that's the one weight matrix we're interested in. And the hidden layer you don't observe, but the hidden layer is used to encode correlations. And so you're interested in the distribution of the visible layer, which is obtained by integrating out the hidden layer. And of course, since everything is Gaussian, the distribution here is also Gaussian. But now there are correlations between all the nodes on the visible layer. This all the visible nodes talk to each other by communicating via the hidden layer. If you integrate out the hidden layer, then this kernel K is given by this form. So the mu squared is the mu squared is from the visible layer, and then if you integrate out the hidden layer, you get this WWT matrix. And if you use the singular value decomposition, this is expressed in terms of the eigenvalues or singular values of the. Now this is kind of interesting on its own, but not the topic of the talk, because if you look at this long enough, then you realize, of course, that your theory on the visible layer is a Gaussian field theory. All the information, because it's contained in function. And in the hidden layer, this operator, or the eigenvalues of this operator have a very specific form. Namely, they're all mu squared, and then minus a term which comes from the singular value. So mu squared minus it's sigma h squared times psi1 squared, psi2 squared, and so on. And if you have less hidden nodes than visible nodes, you only have capital N singular values, so all these equal to mu squared. Now, if you look at this long enough, this is actually a ultraviolet regulator, so to say, because the eigenvalues of this matrix are always bounded by mu squared, and then they are lowered by amount sigma squared times psi squared, up to the point where you have no singular values left, and then all the remaining eigenvalues would equal to mu squared. So in other words, basically they are mu squared, and then you go down, and this is an absolute cutoff, so this is like a UV cutoff. And so if you choose the number of hidden layers less than the number of visible layers, so okay, and when you train the model, I'll say this in a minute, when you train the model, you try to do these things. So numbers is not visible layers. It means you cannot reproduce all the eigenvalues. So you equate some of the eigenvalues to the ultraviolet cutoff. And in the same way, if your target data has eigenvalues which are larger than mu squared, then again, you will not be able to reproduce those. So for all practical purposes, both NH and mu squared are ultraviolet cutoff for this model. So let's so this side demo use this Gaussian RBM to generate pictures from the MNIST, so train on MNIST data. So MNIST is 28 by 28 images. If you can then compute the 2-point function, which is all you have in this model, averaged over the MNIST data set. So this is a 784 by 784 matrix, and so there's 784 values, and they are put here in the opposite way because they are inverted here. And so this is the infrared part of the spectrum, and then there are many, many ultraviolet eigenvalues here. And so this, so one way to think about MNIST data is actually it's a set of eigenvalues, and there are a few infrared eigenvalues and then many ultraviolet eigenvalues. But of course, the number of eigenvalues finite because I have actually the number of values determined by the size of the pixels. If I now train the RBM on this MNIST data set, and I say choose this RBM mass to be 100, then indeed it really acts like an ultraviolet cutoff. So this picture is now really the eigenvalues, so it's inverted, and then you see that the infrared eigenvalues are the ultraviolet ones are here, which are not able to learn more eigenvalues than your ultraviolet cutoff mu squared. So in that sense, it's an ultraviolet cutoff. In this case, the number of hidden nodes is equal to the number of visible nodes. If I reduce it, well, I say all the times I, but I mean, really, then again, you filter down the number of eigenvalues in the spectrum. If I reduce the number of hidden nodes push off here, then I only those. And the quality of, so the generative power obviously is strongly reduced if I don't include enough eigenvalues, enough eigennodes. But as was mentioned yesterday by Art Louis, that you actually don't need that many eigenvalues or eigenmodes here. The order of around this number is enough to really generate the very recognized. To go small number to lose the generative power. Okay, so this is one way to think about the restricted Boltzmann machine. But now we don't want to use it for generative AI. We want to look at this Dyson-Brownian motion and see whether the random matrix features are there. So this model is updated with some stochastic update. It's not exactly saying to send something. And so you want to maximize the likelihood or minimize the KL divergence. So this is the update rule. And this is stochastic. because these expectation values here are sampled over the target data and then the model updates. And so we have a stochastic update here for a weight matrix and expects these random features. Now, how do you see them? And this is maybe the point that if you look at this data here, there's so many eigenvalues, it's quite hard to see the random matrix features. And so what we did is let's take a very simple model. So instead of having a model with 100 eigenvalues or more, we want to train target model only of 10 values, and those are degenerate. And so we can exactly see what is happening. So our goal is that the RBM is trained to reproduce this eigenvalue distribution. That's the goal. And because there are only so few, we can actually really, follow what's. And so this is Pasteur distribution. You sample your weight matrix, you compute these eigenvalues X, and as time goes on, indeed the system learns, and so the dashed vertical lines are the eigenvalues of the target distribution. System learns, and you learn these eigenvalues well. So that's the very big picture. But of course, the question is, does the eigenvalues? These eigenvalues are exact here, so the dashed lines. So why is it a distribution? Why doesn't it learn the exact spectral lines? And RMT, so this Dyson Brownian motion description makes some very precise predictions, namely that there should be eigenvalue repulsion there because of this Coulomb term. And that's why we had these degenerate values in the target distribution. If this Coulomb term is really there, it's really generated by the stochastic update, you shouldn't be able to learn degenerate eigenvalues of the Coulomb portion. And so in the rest of the talk, we'll analyze this learned spectrum in detail and see whether it actually learned the target spectrum or whether it inherited these RMT features. So what are the predictions? So as I said, we have target solution such that there are the combinations of two degenerate eigenvalues. So it's convenient to just look at two degenerate eigenvalues to start with. So imagine that there are only two eigenvalues, and the target distribution is degenerate, and the Coulomb gas distribution takes this form. There are just two integrals, so these two eigenvalues, x1 and x2. There's a Coulomb repulsion. Take a simple Gaussian, and both values should become equal to kappa. We know that that's not possible because of the Coulomb term. So how can we detect this eigenvalue repulsion then? Well, there are two ways to do this. One is called Wigner's surmise, and the other one is called the Wigner semicircle. The Wigner surmise says, well, let's look at the level spacing. Let's look at the distribution of x1 minus x2. And if there is this Coulomb, you can basically do an integration that then tells you that the distribution of the level spacing is given by this particular distribution here. The linear separation is S dx is 1 minus x. And so if the eigenvalues that are next to each other, they should satisfy this Wigner surmise. And then there's a mean level spacing that comes out. So we can do this. Oh, this is still more and more equations, basically. Yeah, so there's the universal prediction, actually parameter-free prediction. But if mean level and you Wigner surmise in terms of this normalized level spacing, you get a universal prediction. So this is one of the universal predictions of random matrix theory. And so what we can do is do many RBM runs, vary the stochasticity by varying the mini batch size, collect data, vary the learning rate, and see what comes out. And indeed, lo and behold, what comes out is indeed Wigner surmise distribution. So the level four degenerate pairs. So these are four pairs. And for each of them, there is a curve here that fits the data more or less. If I then rescale it with the mean level spacing, which is different in all these four cases, this data indeed nicely collapses to a single curve. So that shows that there is this universal repulsion between the eigenvalues that are close to each other. Now the whole algorithm didn't depend independently on batch size and learning rate. And so you can do these simulations and vary learning rate and batch size independently. And what you find then is that indeed this mean level spacing collapses to a dependence on learning rate over batch size, exactly what the theory predicted. So if you go around the potential, the variance in the Coulomb potential should go as alpha over batch size. The mean level spacing goes as the square root of this, and then there's some non-universal terms as well. And so the circles here are obtained by varying the batch size. Crosses are obtained by varying the learning rate. If you plot them in against this ratio, the data falls on the curve. So indeed, this stochastic overlap is Brownian prediction. You can also look at the spectral density, so not at the distance between nearest eigenvalues, but at the the spectral density, which basically tells you about all the eigenvalues. And for two modes, there's an analytical curve which you can evaluate. It's not, it looks like a Gaussian, like here, but it's not a Gaussian. And when you plot it, it's broader than a Gaussian. And we can do each generate. And so this is for one pair of modes, and this is the fit. This is for another pair of modes, the fit. And indeed, the data is extremely well described by this random matrix spectral density. And it's also clearly not a Gaussian, so this is the Binder cumulant. It should be 0 for a Gaussian, but actually it's very close to the value you get for the bigness semicircle. And so the data is again described by the random matrix prediction and not by the target value. It could be the dashed line. Again, you can vary learning rate and batch size and see how this width of this bigness semicircle depends on each of them. And again, there's a data collapse because it should only depend on the ratio and not on each of these separately. And the relation from the normalized and vertical is one of the things. Again, there's complete consistency between those. So in other words, the random matrix description works extremely well. Here, up to now, I was only looking at two eigenvalues that are close to each other. If you look at all the eigenvalues, there is still this repulsion because the Coulomb term repels all the eigenvalues, not just the nearest. So the current eigenvalues normalized by the target eigenvalues. And you can see for non-zero learning rate, non-zero, non-infinite batch size, the learned eigenvalues are not equal to the target ones because of this Coulomb repulsion. So it doesn't learn the target distribution, it only learns the target distribution in the limit that the stochasticity goes to. And this means there is no perfect learning, quote unquote, unless the stochasticity vanishes. And so if you do your experiment and you look very closely and you have a finite learning rate and a finite batch size, you should observe that there is some deviation from your target distribution. Yeah.
Do you think that actually might solve this? Because, you know, that very much. And then often the cases you see your collapse, so there's low rank bias. They are often a sign of generalization. And what you showed in the graphs correlates with somehow the dynamics with large learning rates forces in your network to focus on a few features and then often may actually help in general.
That's exactly why I put this comment here. this would not be there, this data here, for instance, in this distribution would just all collapse to this dashed line, and then it would be quite hard to generalize, because if you have a slightly different data where it's not exactly here, you wouldn't know what to do, but the eigenvalue repulsion keeps this broad, and that allows you to generalize easier. I think that's, indeed, that's, it's hard to really quantify this, but that definitely in mind that the notion to the stochasticity actually allows you to generalize easier, because you're not exactly learning the target distribution, so you're not overfitting. The stochasticity expressed as this ratio here prevents overfitting. Yeah, so basically this confirms that this says. Now I can still talk for another half hour, but let me go a little bit quick. This is kind of a nice mathematical physics problem, which you can do in this case. We know the drift analytically here in RBM. So Ki was the diagonal part of the gradient of the loss function, and you can write it like this. So this value and went to 0 the exponent. And you can integrate it, so you actually have this potential. So in the Coulomb term up there is this e to the minus the potential. So this is the potential. And so we actually know the distribution that is being sampled from in the equilibrium case. So if I only look for one mode, so I drop for now the Coulomb repulsion, I'm basically looking at this theory. And we know how to solve the Fokker-Planck equation. This goes back to what I said yesterday. We know the stationary solution. I'll be a bit quick here because it's a bit precise. Basically, you can describe the dynamics in terms of a Fokker-Planck Hamiltonian. Fokker-Planck Hamiltonian can be written essentially as an L dagger times L operator. That is good because it means that your process will converge, because this is non-negative ground. So the stationary solution is the ground state, which is L on the ground state is 0. And if you look at this potential, so the potential that I drew here, it's actually a double well potential in a finite interval. And so the kind of nice thing is that you can compute everything here. So you can map the problem here to a quantum mechanics bound state problem. The potential at 0 is up 2 squared, which is the highest value you can get. And so to completely solve this this problem, you basically have to solve a bound state problem in a double well potential. And you can do that.
Can you say what L is again? I missed that.
Huh?
Can you say what L is again?
Yeah, so if you can rewrite the Fokker-Planck equation. This is the one I showed yesterday as well.
Okay.
If you factor out square root of the stationary, you can write the Planck equation as a Hamiltonian problem in imaginary time quantum mechanics. And this Fokker-Planck Hamiltonian is of form L dagger L, like A dagger A, which means that the spectrum is non-negative, which means that this Fokker-Planck equation converges. But also it means that the ground state given by L on the psi is 0. So you're guaranteed that there is a stationary solution that and we know the solution of L on something is 0, because that's essentially given by the other square root this part, so we get full stationary.
I was wondering the dynamics of the Planck equation.
Yeah.
And you need some symmetrized Hermitian version of the Hamiltonian. Get it by itself.
Yeah, I think it's the other way around. I would say if you start with the Fokker-Planck equation, and this showed this yesterday, because this is essentially that stochastic differential equations converge to the equilibrium solution. This is the proof that this is, because this is generic, this is not specific to this model.
Trying to photo of that slide.
Which one do you want? This one?
This one.
Yeah. And so if you think about this now, this quantum mechanical bound state problem, this is well, this solve that quantum mechanical bound state problem. This is the ground state. And the point is that if the level, so G squared is the level of stochasticity, and G squared is learning rate over batch size. If you make the level, if you reduce the level of stochasticity, the wave function becomes more narrow around the target value, and so you get better predictions. Say you and the limit, obviously, by alpha over batch size goes to 0, this becomes a delta function and for the target value.
That's right. That's the ground state.
That's the ground state, yeah. So this distribution, if you combine them with the Coulomb term, basically gives you these distributions.
Can you get, I mean, I guess you would be excited.
Yeah, but the excited state is decay in time. So if you need a state. In fact, I have a movie. I only have one movie in this talk. So this movie is doing exactly this. So here I solve the Langevin equation for the eigenvalue, for all the eigenvalues, putting in the Coulomb rotation, starting from the Marchenko-Pasteur distribution. And if you play the movie, then you will see indeed that you see stochastically, and it learns the target data. It switches to the vertical dashed lines. It does not learn it exactly because of the eigenvalue rotation, but it fluctuates around the right value. And this goes back then to the question about generalization. Basically, so if you now generate new configurations or new pictures, say from this trained network, you will get those. Okay, so that was this RBM. So this model is essentially completely solvable. You can understand everything, and it exactly. So the update is the standard contrastive divergence. We didn't change anything, but yet it satisfied the whole Dyson-Brownian motion predictions, basically. That was the thing. If you go a bit more complicated, so this is the last 5 minutes or so, last 10 minutes, 5 minutes. So in more advanced architectures, what happens there? Well, you have many more weight matrices. So, okay, which one do you want to look at? The target spectra are not known. In fact, you do not even know whether it exists. Is it correct to say that if I have some there a stationary solution that is the stationary solution? Even that, I don't think we know. Or maybe we do after this workshop. So what is the loss function landscape? It's not as simple as these two target lines. We'll do a very brief empirical study using transformers, which is on the archive. And so we can study, the these E matrices in the different layers. And so that's what we do. This one uses Adam optimizer. We'll also show here, which makes it's a bit more complicated to actually look at this step size over batch size dependence because it's all adaptive. But still, we can see some of the key features. On the architecture, if it initialized from a normal distribution, then X satisfies the Marchenko-Pasteur distribution. So this is the eigenvalue distribution as a function of X, square root of singular values, satisfies the Marchenko-Pasteur distribution. It's initialized not from a normal distribution, but from a flat distribution, which means that this sigma width here is 1/3. Definition. If you now start training the transformer, you can follow how this eigenvalue distribution evolves in time, and you find that it kind of starts to deform. So the Marchenko-Pasteur distribution is still given by this line here, but more eigenvalues appear at higher values of X. And in fact, it has a power here. we can do is see which part of the eigenvalue spectrum is still captured by the Martenko-Pasteur distribution and which part goes into a kind of power tail. And so the fits here are fits to a Martenko-Pasteur distribution where the width is a parameter. So width goes from 1/3 to 0.6 to 0.76. So the Martenko-Pasteur part broadens, and the part by the here is 0.9, which means that this is about 10% have moved into the higher part, and here is 0.8, or 20% of the eigenvalues moved into the higher part. And so you can follow this evolution as a function of a training time for the different layers. So these are the K matrices for 4 layers, and you basically find this kind of dynamics that the part that is described by the Martenko goes down. So, and the MP distribution itself broadens essentially due to Brownian motion. So this is a kind of dynamical description of learning by looking at how the singular values or the eigenvalues of the weight matrix evolve. If you only look at the nearest neighbor eigenvalues, so the level spacing, then you will find that essentially at all times it's still described like 5,049, 5,000. And so this shows that the universal fluctuations at very short distance are still described by random matrix theory and the big assumptions. So that shows that that aspect is still easily visible in the evolution, whereas the emergence of this power law is more complicated to explain. That has put up a whole lot of other questions, namely, what is the final target spectrum? Does it exist? It has to do with heavy tails, which is also noted in this quite well-known paper by Mahoney. There's heavy tails here. What's the power of the tail? If the fact that part of the spectrum remains Martenko-Pasteur, it means it hasn't really changed, so is that important or not? So that is basically what I wanted to say. So the main universal features, which are described by random matrix theory, they are visible if you look close enough. And it leads to a fundamental limit on how precise you can learn, because eigenvalues that are too close will rebel. If you go through the algebra, it turns out it only depends on learning rate over batch size, as this linear scaling rule suggested. But one question about emotion is present at kind of microscopic level, but how does it manifest itself in more complicated architectures, and what universal features beyond level recursion can be seen? Okay, thank you.
Back to your bigness minus plot.
Are you saying the reason that we see the Wigner-Mice, it's really about the dynamics of SUD that bring us there? So there can be no such model that we would be getting for so many type statistics. It will always be Wigner-Mice because of the repulsion induced by SUD.
Yes, I think that's what I would say. I'm looking at
could there be a regime which would get so many statistics?
I don't know whether such a regime exists, but basically, yeah, the line of the talk is exactly like this. At microscopic level, this SGD is Dyson-Brownian motion, which leads to the Wigner surface.
Did you investigate the Hessian with respect to the loss, with respect to the input? Because we saw Wigner there as well. I'd be curious how some of your analysis extends to that case.
Yeah.
And if you had any interesting numerical methods that big. Because,
yeah. Did you write? Okay, I don't know your name, but were you in Bristol?
No, but that was Nicholas Baskel was my co-author.
Right.
Okay,
so I glanced at your paper. No, we didn't look at the Hessian. That's right. The training dynamics.
Surprising.
No, because the training dynamics. So where does the data come in? You take some mini batch updates, basically, but that will depend. The drift term will depend on the vehicles there. But that's it. The other parts are kind of universal. Yeah.
If I simply did exact gradient descent, as far as you're concerned, I would head straight down, right? Because
Yeah. So you would not get this broader. This distribution would become narrower and narrower, and you would reproduce the target data. And the Coulomb repulsion, which leads to this propulsion, would go reproducing target spectra.
the thing is, the two effects, right? One effect can be, I'm heading down and I get trapped in local minima over the theory, nothing is kind of a theory of sampling error rather than a theory of what the local landscape is.
Exactly. So the landscape here is pretty easy. Essentially, is this. This is the potential in which each eigenvalue involves. It's pretty easy to find the local minimum. So our loss function is not like a huge landscape. Yeah, but the stochasticity keeps it.
Yes, when you're looking at the sort of variance in this mini batch, then you are assuming that it's Gaussian fluctuations in this, which I guess it is an assumption. I mean, I make assumptions.
No, so it's an assumption in the analytical work,
yeah,
but not in the numerics. In the numerics, nothing is assumed about the the numerics just use standard contrastive consistent contrastive divergence. So in the actual numerics, no assumption is made. This is an update. The brackets here are all the mini batches, as the way I explained. But that's it. Nothing is, no noise is added.
but I guess in the sort of Coulomb stationary distribution.
There are some distribution here, which essentially is which leads to this scaling. Yes.
Technical thing which you might find useful is if you're looking for random matrix statistics, there's this more recent method, you take ratios of neighboring differences, because then you don't have to estimate the mean level spacing.
Yeah, so the mean is used here. Normally you would do the spectral unfolding, and then the mean doesn't appear anymore because it's kind of.
And this was literally invented by my former colleague David using with the Morganessian, which is that, prior to that, you would go around trying to estimate the mean, you had to normalize. But what they observed was that if you take two successive differences and you take the ratio, the mean goes out of it. And then there's a number of various so that you will often see used in the
Okay, we can look at that.
convenient.
Yeah, I should say also to comment about the Hessian. So random matrix theory has been used, not quite a bit, but to some extent before to analyze weight matrix distributions. But we think not Dyson-Brownian motion description where the dynamics is important has not been used to this extent as we did here. But it has been used to analyze just weight matrices after training and see how they